So this is a follow-up on the problems we did on Friday on the sheet, which we checked. We were checking them.
No, we already did.
Yeah, that's what I was saying.
Oh, okay.
I said, do you remember checking them?
Yeah.
Oh, yeah.
Okay, and it was kind of right towards the end of class, so how did they go? I don't remember if I asked. Sorry.
Oh.
Probably did.
Good.
Okay. Well, for this, I like this kind of problem because first you have to write equations and then you need to solve them. And in this case, do it twice. So let's do M instead of V, so we have sort of a context for each person. What's his equation?
1 what?
180 is equal to 1,000. Open parentheses, 1 plus. No.
It's perfect.
Oh, yeah, that's right.
Good.
That's
E to the
0.04475. Oh, that probably.
okay. How about the other person? Peter. Good. All right, so both of these are trying to reach 1800. What are we really trying to compare here? Can you put that in words?
The years till they get to.
Well, yes, I understand we're trying to solve for years, but I'm saying, like, why is this even something we're trying to solve for? What is being compared in terms of its influence on the total?
The percentage and the initial amount.
Yeah, like which one has a bigger effect? The compounding percent or initial investment? What would you have said before you did the problem? So the higher percentage? Okay.
Peter.
And you said Peter? Okay. If you store or keep those equations in there, because let's check for 1800, and I'm just going to do this. Let's check it for 1800, and then, which we know is going to be in the short term, but then maybe run it out to like 10,000 and see if there's one that makes a bigger difference. Okay? We'll see if it's the same as short term. How do we solve this? Okay, so divide off A or P. Hmm?
And then natural log.
Yeah, good. Natural log to get rid of that log. Or get rid of that exponent, excuse me. Okay, so remember we learned on Friday to undo an exponential, we do a log of the same base. To undo the log, take the exponential of the same base. Okay, so this will leave us with 0.0425t. And we're saying e to some exponent gives us 1.5. So we know that has to be, it's not even a full 1, right? So we can just take that to the calculator. 1.5. So 0.4054, 0.4055, let's go there. Okay, and then just divide. It's going to be pretty close to 1. Or 10. 10? Dang, that's a long time. Almost 10 years. Okay, the other one basically solves out the same, only we'll divide, well, it solves the same process, but we divide by 1,000 and then eventually we divide by 0.047 instead. So let's just do that and I'll put it up here. So we get 1.8. I should have did natural log first. Natural log 1.8 and then divided by 0.047. So 12 and a half.
Yeah.
Okay. That is, I'll be honest, that's longer than I thought. Okay, so let's now do the same and solve for, let's say, $8,000 and see if it continues to be true that Michael's slower in getting there. And you can just run the numbers on your calculator. So I said 8,000.
Hey, how much does he want to make now?
I'm doing $8,000 now.
44-ish. Michael should be putting in money every month.
Yeah, they both should, huh?
Oh wow, they're kind of close.
Alright, keep doing that. Natural log of 8.
.0475.
Alright. I got 44.6 and 44.2 years. What it took to get to $8,000. So it was still Peter, but definitely by a smaller margin than it was for in the near term, right? Like that was it 3 or yeah, 3. It was 3 years. That's a lot different initially, but then further out it's not too much different. And then eventually, do you agree that it would pass and Michael would be faster?
Yeah.
Okay. So I think, 44 years is your working life. So that should kind of point out that if you can put more money into some kind of an account earlier, that growth over time does make up for a less interest rate if you can. Okay? So that's cool. How does this whole problem go? Any iteration of it? From Friday after the weekend? Feel like it went okay? So writing and solving, that's a big deal. All right, grab your notes. We're going to move into just quickly on log functions. And I showed you the graph of that on Friday. It looks like this. The actual graph. The orange one is which function rule?
That's if it's not the base is not
Well, but we saw if we have a negative base, remember it was that kind of dotted one that sort of diverged. So which wasn't exponential. So the orange one is the exponential base, right? Like 2 to the x. I don't know if you can see it, but it says 2 to the x. And then the blue one is its inverse, which is log base 2 of x. So big ideas. And really this is what I want you to focus on. Remember that the exponential function had a horizontal asymptote at y equals 0. It never crossed the x-axis. It never even got to it. So you can't plug a number in for x to make this be 0 or negative. Remember that? Those are some big exponential properties we learned last week. Okay, and then it, of course, grew from there pretty fast. Okay, the log function, how would you describe its nevers, like we just did with the exponential one? Okay, which means what? Okay, what did you say? There is no y-intercept. Good. Okay. So let's think of some technical terminology. In this one, what is limited between domain or range?
Range is limited because it's anything from 0 to infinity.
Yeah, so this one, we're talking about output values. So the range is limited. It's 0 to infinity. Okay? How about that one, the blue one?
Domain.
On that one, the domain is limited. So it's different. Now we cannot plug into the log function any values less than 0. In other words, input values. What's its domain?
Zero
0
to
to infinity. What's its range? The log function.
Negative.
So it's an infinite range, but a limited domain, or restricted. Okay? So that's an important thing to distinguish. With our exponential function, unless we do something like 2 to the x minus 5, that's going to generate negative numbers. But just for the exponential function itself, we will never output 0 or negative values. With the log, you cannot input 0 or negative values. That's a big difference, right? Because when we're going to solve these, that means we're solving different things. In fact, just for fun, put in one in your calculator, like just do log of negative 5, or log of negative something, and see what yours says as an error code.
Not a real things.
Okay? So it is sort of analogous to this. Like we had a way around square rooting a negative number, but it was a non-real result, okay? So when we look for domain restrictions, like we've done that before, what was the primary use of a domain restriction for us so far?
I don't know if that's the question that you asked, but that's the answer.
Primary occurrence or use of a domain restriction? Vertical what? And poles. So it was in our rational functions where the denominator could not be 0, right? Well, this is another one. You have to restrict domains that create negative square or even roots. And now we have another one where we have to restrict domains to not create negative logs. That doesn't work. Or logs of a negative number. Those of you going on in math will learn more about when we do that, but it's good to start locking that in now. Okay, well, we can modify this graph just like we did with the exponential one. For example, if we add 3 inside of the log function, what do you think that does?
Moves it to the left.
Yeah, okay, so now that graph would shift to the left 3. But what shifts? Like, what is that shifting? It didn't ever have one, right? So now it does. This particular one has a y-intercept. Because if you think about making x 0, that's just really log base 2 of 3, which is like 1 point something, right? 1 point something small. So now it has a y-intercept. But what are we moving left and right when we add something inside? Well, but this didn't have a horizontal asymptote.
What makes it negative?
It's the vertical asymptote, right? So you're on the right track. So now, instead of being the y-axis, that's not a very good one, but now our asymptote is here instead, okay? So what moved the horizontal asymptote in an exponential function? What letter? Thinking of our transformation letters, A, H, and K, which one moved the horizontal asymptote in an exponential? No. K did, right? In an exponential, here, let's go back to this. K shifted the orange graph up and down, which moved the horizontal asymptote with it. Okay, now the blue one has a vertical asymptote. What moves it? H moves it left and right, which shifts the vertical asymptote. Okay?
Favoritism.
Huh?
That's great favoritism.
What's favoritism?
I said H, and you're like, no, that's wrong.
You said H for the blue one? Sorry.
What?
There's no favoritism.
Oh,
Except for I just like some students better than others. Just kidding. How about this one? Where is it moving?
It's
The left.
Nope.
Up and down.
Nope.
Oh.
Yes, it is up and down.
Okay.
Okay, where? Here's our parent. Remember, these kind really benefit, I think, by graphing the parent first. And if not, I mean, if you don't need it, that's fine. But So that's roughly a parent function. Where does it go when we add 4 to natural log of x?
First you need to move your horizontal asymptote up forward.
It doesn't have a horizontal asymptote.
Well, is it the spot that it's like avoiding is gonna be 4
No.
instead of 0? Oh. It's gonna cross.
What is it avoiding?
The y.
A vertical line x equals 0. So if I take this thing and just pull it up, does it change the fact that it's avoiding 0? On
No.
the x equals like the y-axis. X equals 0, which is the y.
It's no.
Does it change if I shift that up? No. Is there a horizontal asymptote for this function? No?
Yes. Yeah.
So it's approaching a horizontal line that it will never reach.
Oh,
It's very possible.
It's not. There's not a horizontal. What? Okay. Everybody, use your arm to make horizontal. Does it approach a line like this that it never reaches?
no.
Well,
No.
when it gets and you're moving very slowly.
Well, it's gonna just keep going up. So all horizontal lines will get crossed.
Well, it'll still be horizontal, but
It doesn't do this. It doesn't do that.
I mean, we can make it do that.
We can't.
You just
All right, let's just put it in here.
Okay. Oh.
By the way, if you do graph it on, Desmos, you have to go dig in here, I think. Log, unless I'm just missing it. There it is. Natural log. Okay. So see how it just keeps going up?
Mm-hmm.
Well, I mean, to you, does it look like that, or does it look like it levels off?
it still goes up a little bit, but like from right there, it's not crossing the line. Like it's just getting closer. Don't keep going, please. Don't keep going. Don't.
You're saying?
Yeah.
Well, it's not passing that one that's above it. See, so
It's
like
gonna.
it's still.
See, look. It's gonna eventually, but.
Well, like.
It looks pretty.
Hey, look at that. It's pretty much straight. Boom, down. See,
Okay,
straight.
but now we're above that line.
No, it's
Still going up.
been above that line. See,
Nuh-uh.
see, I have to like very conspicuously put away my glasses so I can see it.
See, now it's getting closer to that line.
I can't see it actually.
Alright, it's going up. Alright. Yeah, I can add
Leaves
the
it
4.
off at the most level spot.
Actually, can I just add the 4 to this one? Plus 4. So see, it just moves it up, but it doesn't change its character in any other way. Right? Did you see that?
Actually, I was putting off my glasses, so it looks the same.
Alright, what?
Yes, you are.
So it's
I'm very.
log and plus.
Okay, so guys, it does the same thing as always. K shifts the whole thing up and down. H shifts it left and right. That's the same as it always has been. The difference is with this one, we have a vertical asymptote. So the vertical asymptote changes with H, whereas before it had a horizontal asymptote that changed with K. Otherwise, it's the same. Like all the transformations are the same. What would happen if I put a 10 in here, out front? Like A is 10.
It would. Right. I feel like it would be like it would.
Okay? Well, keep your eye on there.
-10?
Keep your eye on there. 10. What did it do?
It
vertically
stretched it.
stretched.
A lot, right? It shot up faster now. Okay? What if we put a 0.5 in there?
It'll go fast.
It's gonna compress.
Okay? So like squish it down a little. So see how it's all the same?
Yeah.
I'll put I don't know, what do you, let me tell you and you tell me what to do. I want this to have a vertical asymptote of 2.5. Tell me what to type in here.
Plus
Minus 2.5. Okay, do you see how it shifted to the right now? And now that thing dives and avoids anything left of 2.5.
See, it's crossing it, so it's like.
It's not either.
I see something.
Alright.
It's not like that. This is something
Are you good on that?
Yeah.
Okay. Let's go just make a note about it.
absolutely rad.
Do you think the graph of a log versus natural log looks different?
Not really.
Yes.
What's the difference between the two just in speaking about it?
So log is base 10, and then natural log is.
So what do you think will, I'll put them both up here. There's natural log. What do you think will look different about log base 10?
It's gonna be. It's gonna like.
Okay, so I want you to think of the inverse. Remember? Look at me. If we reflect this over the line y equals x, what is the difference between 10 to the x versus e to the x? Because this will be the same, just reflected over y equals x.
It goes up faster.
Which one?
The 10.
Okay, so he's saying if this was exponential, 10 to the x would go up faster. It still goes through 1, because 10 to the 0 is 1, but it shoots up faster after that. So if we think about a steeper curve being reflected, will the, whatever color this thing does, will it be below this red line or above it? Here, we're going to take votes. What do you think? Above?
Like above.
As it's below, and we're starting to apply to us.
It rhymes with
It should be below. Did you guys just change your answer for him?
No, I asked him what you said.
Oh, you just asked him? It's below.
It's above it.
Partially below, you're right.
See, no, it's above it technically.
For a moment.
So
Yeah.
it's still
From
right.
0 to 1, it is above, you're right.
Technically.
Okay.
it would be below it.
But is it super different?
Yeah.
I mean, characteristic-wise, is it different? No.
Wait, where did it?
Where did what go?
I thought you said it was gonna hit one and then shoot up.
That was when we were talking about exponential. 10 to the x.
Oh.
Goodness gracious. You guys ate too much sugar yesterday.
I do
I did
not
not
like have
eat
any.
a single piece of candy.
None?
None.
Well, good for you.
You know what I ate? I don't like chocolate cake and Buddy Buddy.
Chocolate cake. That's
I don't like
something.
cake either. I don't like cake. I can't have dairy, so I don't eat it.
Alright, so let's sketch the graph. We'll put in some characteristics about the transformations and stuff.
Oh, we haven't gotten any more lately.
Okay, where does it cross the x-axis? Did anybody notice? Okay, well, let's ask the question. Let's do log, just plain old log. Log of 0. What's the base for this log that I just wrote? 10. So what power of 10 gives 0?
1.
Zero? No,
Nothing.
zero's one. Oh.
Oh, I should put, sorry,
Yeah,
that's not 0.
yeah, that's not.
X-intercept, I have it in the wrong
We're
spot.
just gonna talk about how much it is.
1.
It's 1.
Okay, there we go.
Yeah. So put a 1 there. It's Jazzy's
said
fault.
that 3 times. Mr. Atkins, they won't listen.
What?
Ah!
I'm listening. Did you say 1?
Yeah.
I heard you say 1.
Yeah, like.
I like ours. Did
Still
you
favorite.
say the one
Myself.
So I heard you say 1.
I got eaten. Maybe that was made up. I thought you said how it was Jen's fault. Oh.
Now, again, this is before any transformations. I guess we should write that, before any transformations. Okay, so you can't plug in negative numbers or 0. So when we just did our warm-up and we're solving for t to get to $1,800, there are no transformations with that. So when we take log, well, I guess technically in there was a 0.0425, which would be, but just be aware that when you're inputting a log, you can't put in negative numbers because of this, unless there's some kind of plus or minus in there that would compensate for it. Okay, if in terms of transformations, oh, you know what, before we write that, over here, let's remind you that there's a vertical asymptote now. Which is going to be at x equals h. So just in our parent graph, like log, just common log of x, what is h? Like if we graph, we did actually just graph this, log of x, log base 10 of x, what's h? 0, so that's what we're putting up here, right? Is a vertical asymptote of 0. Good? Okay. Do you need a break?